Okay, we can start from where we left last time, so that we had covered, first of all, the case, the basic reasons why we study quantification. We have discussed applications in machine learning, data mining, natural language processing. We have discussed how to evaluate the accuracy of quantification systems. And we have discussed the evaluation protocols that we need to do in order to create data sets that allow us to evaluate quantification systems. In part 4, Alejandro has covered actually the methods based on supervised for solving quantification. I'll start now, progress through advanced topics and conclusions, and after that, Alejandro will give you a hands-on session on how to set up quantification systems and apply them to your own data. So what do I mean by advanced topics? Okay, so I essentially mean a number of topics in quantification research that have been studied, but we haven't covered up to now. Up to now, we have essentially covered the single label multi-class case, which also encompasses the binary case. That means quantification when we have a number of classes higher than 2, and when we need to pick exactly one class for each data point. Okay, so this covers many applications and is in some sense the most general and most studied case. But there are a few other cases which we haven't covered here. So for instance, we haven't covered multi-label quantification, which is the case when each data point may be assigned to 1 or to 0, 1 or several classes at the same time. We haven't covered ordinal quantification, which is the case when essentially we need to assign each data point to a single class, but the classes are ordered. Okay, so there is a total order defined on the set of classes, such as when we have, say, 5 different classes on which to evaluate product reviews, and one of them is very negative, the other is negative, neutral, positive, very positive. So there is a total order defined on these classes. We'll cover in some detail, as much detail as possible, multi-label quantification and ordinal quantification in the next few slides. Instead, I will not be able to cover the other topics listed on this slide, so I'll just tell you a little bit about it. So regression quantification, what is this? In a sense, we might say that single label multi-class quantification stands to single label multi-class classification, like regression quantification stands to standard regression, metric regression. Okay, so essentially it's quantification when each item needs to be assigned not a class, but a value from a real valued interval. Okay, so it's what are the applications? Okay, so there are not terribly many applications for this, but you can probably think of some. Okay, so think of you remember when we discussed the application to detect no-shows on airplanes. Okay, so to detecting, say, that 20% of the seats on a flight will be no-shows. Okay, so determining the percentage of seats that are occupied. Well, think of the same airline problem, but think about cargo. Okay, so not passengers. So, airlines have cargo flights when so where the goal is to move goods from one airport to the other, you know. And in this case, you know, people book, I mean, merchants book shipments, you know, like passengers book seats on a flight. And when a merchant books a shipment, books for a certain quantity, you know. And in this case, a merchant can, let's say, overship, undership, you know. So maybe a merchant books for 250 kilos, but actually ships just 200. Okay, so the merchant had overestimated the amount of cargo that he needed to ship. Or sometimes, you know, a merchant can bring in more goods than he had booked for, you know. So in this case, you know, individuals, which are individual seats for passengers, get replaced by quantities, you know. So you might easily figure out that quantification here has an even more quantitative aspect than standard quantification as the equivalent of classification. Regression, we will not cover regression quantification. There are some pointers to the literature in case you're interested in. Cross-lingual text quantification. The idea here is to do text quantification in a cross-lingual environment. So say we are classifying and quantifying on documents, textual documents. Some textual documents may be written in English, others might be written in Spanish, others might be written in, let's say, very low resource languages such as Pashtun, you know, such as Ahmadi Boro, etc. You know, so it is typically the case that in such applications we have loads of we have truckloads of training data for English, but very few training data for say Pashtun, you know. And cross-linguality aims to transfer the knowledge, you know, that you acquire through training data from a, let's say, a high resource language such as English, you know, to the resource, to the low resource language such as Pashtun. Okay, so suppose that you want to do text quantification in Pashtun, you probably have very few training documents in Pashtun. And because of this, you would like to leverage the training data that you have for English. So this is cross-lingual text quantification, taking advantage, you know, for a low resource language, taking advantage of the training data that you have available for a high resource language. And there is some literature on this too that I can point to you. So quantification for data streams. Data streams refers to the fact that in some contexts, data becomes available in a sort of a continuous way, you know, and at a certain point, you know, maybe 1 or 2 years after you have collected your training data and trained your quantifier, you know, the performance of the quantifier might decrease, okay, because the training data are no more representative of the data that are encountered 2 years later. So this task, you know, quantification for data streams intersects the let's say the field which is called lifelong learning or continual learning. Okay, so here essentially the idea is that to detect policies by which to retrain your quantifier with newly available data that might have become available later, and that is more representative of, let's say, the current quantification needs. You know, there is some literature on quantification for data streams that I can point to you. Quantification for network data. So you might recall that at the beginning of these lectures, we talked about collective classification. You know, collective classification is classification of individual items when these items are interlinked. Okay, so maybe you need to classify a Facebook user. Okay, but aside from his or her own profile, you also know, you also know that there are links, friendship links between this person and other persons that you might want to classify too. So the in a sense the content that you need to classify or quantify on is not the only information that you can use. Okay, so you can also use the linking information and treat the data not as a set but as a graph. Okay. Again, there is some small but interesting literature on quantification for network data. So cost-sensitive quantification is yet another interesting task. Here it refers to the fact that in a number of contexts, you might, different types of mistakes can have different costs or be less or more serious than each other. Okay, so maybe in a single label multi-class quantification task, there might be errors involving a specific class that might be more expensive, more serious than others. Okay, so cost-sensitive quantification has to do with bringing to bear these different costs within quantification. But let's take a look at at least a couple of the topics, which are multi-label quantification and ordinal quantification. So multi-label quantification is sort of short for saying multi-label, multi-class quantification. Multi-class refers to the fact that we have n different classes with n higher than 1, and multi-label refers to the fact that each data point may have 0, 1, or several classes assigned. Okay, so typically, in the past, multi-label, multi-class quantification used to be reduced to binary quantification. It can be reduced to binary quantification by solving the n independent binary quantification problems. That means you take these classes one by one and you build a binary classifier for each of them. Okay, and this is a very let's say we might naive solution and very easy solution. Essentially, this is the baseline that all multi-label, multi-class quantification methods, all truly such methods are must beat. And indeed, it is possible to beat this the accuracy of this trivial baseline. It is possible because, in a sense, it is possible if you try to leverage the stochastic correlations between the classes. Okay, so the relationships between classes that you can detect in the training data. So, for instance, if we have a large data set, we might notice from the training data, that many data points in class Republican are also in the class Golf. Okay, so that you can say, there is a correlation between being a Republican and loving golf. Okay, and so if you can exploit this correlation, you might build a better quantifier for class Republican, and you might build a better classifier for a quantifier for loves golf. Okay, so in multi-label, multi-class classification, it has indeed been shown that if you attempt to leverage these correlations in learning, you can obtain higher accuracy. And indeed, this is what multi-label, multi-class quantification methods attempt to do. Okay, so how could you set up a multi-label, multi-class quantification systems. Okay, so here I will draw examples for simplicity, you know, from aggregative quantification methods only. Okay, so with methods that first require a classifier to assign individual labels to all of the data points. Okay, so we start from a trivial type of solutions. Okay, so the most trivial type of solutions is what we call BC plus BA, binary classification plus binary aggregation. It essentially consists of using n independent binary classifiers, and well, on top of them, you use n different instances of a binary aggregative quantification methods. Okay, so you take, for instance, SLD, the Sarens-Latin Decastecker method, you know, and you put it on top of a binary classifier, and you do this independently for all of the n classes. Okay, so of course, I mean, this is the trivial class of solutions that anybody would pick, you know. There is a slightly less trivial class of solutions, which is what we call MLC plus BA, multi-label classification plus binary aggregation. This consists of, well, instead of taking n different binary classifiers, you take a truly multi-label classifier. Well, I will not cover truly multi-label classifiers here. There is a large literature on how to leverage the stochastic correlations between the classes in classification. But essentially, you take one of these classifiers, and on top of it, you know, you use binary aggregative quantification methods. Okay, so this is possible because a multi-label a truly multi-label classifier returns exactly the same type of output that a set of binary classifiers. Okay, so it returns, let's say, individual class predictions for all of the documents. Okay. Let's look at another less trivial case of solutions. This is what we call BC plus MLA. So that's binary classification plus multi-label aggregation. So here we take n independent binary classifiers, but on top of them, you try to build a truly multi-label quantification method. Okay, so a method that exploits the stochastic correlations between the classes at the aggregation level. Okay, but the best, in a sense, the most interesting class of solutions, and the one that has proven most accurate, okay, is MLC plus MLA, multi-label classifier, multi-label classification, and multi-label aggregation. So that means exploiting the stochastic correlations between the classes, both at the level of the underlying classifiers and at the level of the aggregation policy. So you use a truly multi-label classifier, and on top of it, a truly multi-label quantification method. Okay, let's look, well, this is a sort of a typical depiction of these four possible policies. Here, the dotted lines means that a model, let's say a classifier H here, learns from these labels, and here the solid lines indicate that, let's say, a model gives its output to another model. Okay, so here a classifier provides its input to a quantifier. Okay. Let's look at one such system. How could we set up a multi-label classifier, an MLC plus MLA system? Okay, so we look at one system in particular, which is the regression-based MLC plus MLA that was proposed by us actually in this recent paper. So how does this work? Well, we first take step one, we take a multi-label quantifier Q. Okay, so we take something that we have trained via an MLC plus BA system. Okay, so we take a multi-label classifier, you know, as there are a truly multi-label classifier, as there are several in the literature, and we apply to this binary aggregation systems, say the ones that we have seen in the past class, okay, such as, say, the Serens, Latin, Decalstecker algorithm, this SLD. What we do after this, we put on top of it a regressor, okay? What is a regressor, you know? A regressor is a supervised, let's say, it's a predictor trained by supervised learning that, let's say, returns, you know, takes as input a vector of prevalence values, so the vector of prevalence values produced by this method, and returns another, let's say, an improved vector of prevalence values. Okay, so the idea here is that while this quantification method BA didn't take into account the stochastic correlations between the classes, well, we put on top of it a regressor that does take in considerations these stochastic correlations. Okay, so it takes as input this vector of prevalence values for which the BA hadn't considered, you know, hadn't taken into account the stochastic correlation, and returns a vector of n prevalence values that consider this correlation. How does the regressor, how can the regressor consider these correlations? Well, the idea is that we train the regressor, with a set of pairs, okay? A set of pairs where, let's say, this is the vector of the n prevalence values estimated by the quantifier, and this is the vector of the true prevalence values. Okay, so given a sample sigma I, we take its true prevalences. No, these are training data, so we know the true prevalences. Okay, and we also ask the let's say the quantifier Q, so this quantifier that we had trained via this method, to return prevalence values for it. Okay, so here we have the true prevalence values, here we have the predicted prevalence values, the prevalence values predicted by this system. So this regressor learns to map the predicted, the prevalence values, you know, predicted by this method into true prevalence values. Okay. So it's you might see it as a way of correcting the prevalence estimates of this quantification method. Okay, so why does this system leverage the stochastic correlations between the classes? It does so because the input to the regressor will be a set of prevalence values for all of the classes, okay? And essentially, you can see that this regressor works holistically, okay? It takes into account all of the classes at once. It takes into account a vector of prevalence values, okay? A vector of prevalence values for all of the classes, okay? So it can see, you know, it can, in a sense, which classes are correlated with others, okay? And so the mapping that it builds takes into account these stochastic dependencies. One of the interesting methods, okay, in the beginning we had said, well, we'll focus, you know, on aggregative quantification methods for simplicity. So for instance, we had said BA can be implemented, say, via the Serens-Latin Decker-Stecker algorithm? Well, it is interesting to note that this method can be used also if the underlying method is non-aggregative. Why? Because you might realize here that we are not using the individual labels of the individual data points. Okay. So this is, you might see that it is a fairly easy method, you know. It's a fairly general method because it can be, it only needs a regressor that you can train with any type of regression learner, support vector regression or what else, you know. And you can apply this regressor on top of any type of quantification, multi-label, multi-class quantification methods, and especially one that hasn't taken into consideration the stochastic relations between the classes in the aggregation phase. Something that I would like to notice is also that, well, this has proven the best performing system so far. So it's sort of the state of the art in multi-label quantification. And something that this paper also provides is an experimental protocol specific to the multi-label case, okay? Because it is shown that the protocol, such as the artificial prevalence protocol in the form that we explained it in the previous classes, is not really suitable to the multi-label case and needs to be changed, needs to be tailored to the multi-label case. And this experimental protocol, you know, is something that allows you to generate samples both for testing your final system, but also for training the regress. Okay, so this is just a glimpse into the area of multi-label quantification. There are some other systems that have been proposed based on different intuitions, but these regression-based methods, which is of type MLC plus MLA, so that, you know, tackles, you know, the stochastic relationship between the classes, both at the classification level and the aggregation level, has proven the best performing so far. Let's move to ordinal quantification. So let me recall what ordinal quantification is. Ordinal quantification is single label multi-class. So it's multi-class because we have more than two classes, n classes, which is higher than one. It's single label because you have to assign each data point to exactly one class. And it's called ordinal because there is a total order on the classes. Total orders, as we had mentioned in the past, come up frequently, both in the humanities, in the social sciences, but also in some of the hard sciences, including, surprisingly, astrophysics. You know, astrophysics, where you know, different order classes are used to bin energy levels of astroparticles. In ordinal quantification, misassigning probability mass to a neighboring class is less serious than misassigning it to a faraway class. So let's say if I underestimate class Y1 by 2%, and this 2% goes to class Yn, you know, which is then overestimated, well, this is a more serious mistake than if I do this mistake between two neighboring classes. Okay, so mistaking positive for very positive is less serious than mistaking very positive for very negative. And because of this, the Earth mover's distance that we have seen in the past is a good evaluation measure, because it amounts, the Earth mover Earth moving distance, basically measures also the amount of under prediction and over prediction, but measures, let's say, the distance traveled from these probability masses from one class to the other. Okay. So ordinal quantification has not been researched as much as binary quantification and single label multi-class classification. So there have been some early ordinal quantification algorithms back in 2016. There has been some, well, Mirko Bunse actually discovered that essentially the same task, ordinal, that we call ordinal quantification, exists in the astrophysics literature, where it is called unfolding. This is typical of sciences, because the same problems emerge in disciplines that are very far away from each other, where the researchers were one discipline don't know the researchers of the other disciplines, and so these tasks tend to have an independent development within different disciplines. More recent algorithms have been proposed in 2022, very recently, and so it is one of these algorithms that I am going to look with you here. So this I will look at the work proposed by Mirko Bunse and ourselves too, on ordinal quantification methods which are based on regularization. So you probably know regularization from other disciplines in data science. The basic idea for us here is to take an algorithm for single label multi-class quantification and tailor it to ordinal quantification. Tailor it by introducing a regularization, what we call a regularization, which is essentially a term in the equation that tends to penalize assignments of probability mass, assignments of class prevalence that are, from an ordinal point of view, unlikely. Okay, so what are the unlikely assignments? Well, the idea here is that, an unlikely ordinal distribution, so an ordinal distribution is unlikely if there are sharp differences between the class prevalence value of one class and the class prevalence values of the next class. Okay, so let's say a probability distribution, okay, in which, say, only 10% of the reviews are negative, and 85% of the reviews are very negative, is a bit unlikely. Okay, so we tend to consider likely ones where the moving from one class to the next gives rise to a fairly smooth difference between the class prevalences of the two. Okay, so in a sense, an ordinal quantification method is a method that, let's say, predicts a class distribution, but when choosing between possible class distributions, it tends to favor ones which are smoother, okay, which it considers sort of more likely. And along these lines, several algorithms have been proposed, and which are variants of ACC, PACC, there is a mistake here because it's not PCC, but PACC, and SLD. And I'll show you the basic idea behind this by looking at the ordinal variant of ACC. Okay, so the ordinal variant of ACC goes like this. Let me recall that ACC amounts to solving, let's say, to finding a vector of probability of class prevalence values by solving this system of linear equations. Okay, so where, in a sense, Q is the prevalence estimates that you have obtained via classify and count, and M is the adjustment. Okay, it's called adjusted classify and count because it adjusts the prevalence estimates obtained via classify and count by bringing to bear the misclassification matrix. Okay, so the matrix that says, well, in the training data, we have observed a tendency to assign, assign some documents of class I to assign them instead to class J. So a matrix which is contains the multi-class equivalence of the true prevalence rate, the false prevalence rate, the false positive rate, the false negative rate, and etc. Okay. So in order to solve this practically, to solve this linear system practically, we have seen that we look at least squares solutions. Okay, so we search for the vector that minimizes the difference between MP and Q. Okay, so that minimizes the norm 2 of the difference between Q minus MP. Okay, so these least square solutions, there are several of them. Okay, so the idea is that we try to prefer some among, let's say, among all of the least square solutions of this system, we try to prefer the ones that are smoother. Okay, in order to do this, we introduce a so-called regularization term, a term that penalizes non-smooth solutions. So this is the term, the regularization term, and this is the quantity that needs to be minimized. Okay, so we look for the vector P that minimizes all of this quantity, So what is this term? Well, the idea is that this C is the so-called Tikhonov matrix. Okay, so it's a matrix such that this equation is true. Okay, so minimizing this term, you might notice that this term is essentially the same as this, apart from this tau term, which is a parameter, that in a sense tunes the regularization strength. Okay, so what is this regularization term? Look at this and what it amounts to. So if we minimize this regularization term, we are trying to minimize this sum. Okay, where the class prevalence, this is the class prevalence of the I-1 class, this is the class prevalence of the ith class, and this is the class prevalence of the I+1 class. So essentially, if you take the square of this, it is quite clear that this square will be minimized when there are no sharp differences between these three terms. Okay. Instead, when there are sharp differences between these terms, this square will have a high value. Okay. So, in a sense, by minimizing this term, this regularization term, we minimize, let's say, we give preference to smooth solutions, to solutions whose class prevalence between one class and the following class is smaller. Okay, so this is the idea at the basis of the ordinal version of ACC, but the similar ideas are all at the basis of the ordinal versions of PACC and SLD. Okay, so this is again a glimpse on ordinal quantification, one of our, let's say, advanced topics. Aside from advanced topics, something that I would like to discuss is what the open challenges for quantification research are. Okay, so as you might imagine, quantification has not received the same attention as classification. Classification is sort of the mother of all supervised learning tasks. You know, quantification is let's say a child of a lesser god, you know, so it's a more niche topic, say, and because of these, many open problems still remain. So one problem is to I think that, in a sense, there is a need to investigate more non-aggregative quantification methods. You might have noticed from Alejandro's class that most of the quantification methods that he has told you about are of the aggregative type, and this reflects a distribution in a real distribution in the literature. So there is much more literature on aggregative methods than on non-aggregative methods. But non-aggregative methods are really the true realization of Vapnik's principle, you know, so the principle according to which you shouldn't investigate, you know, you shouldn't try to solve a more general task than the task you need to choose, you know, so quantification is less general than classification. So, I mean, trying to solve quantification by relying on classification, you know, goes against this principle. So because of this, there should be probably more research on non-aggregative quantification methods. Some also, it would be desirable to investigate so-called transductive quantification methods. Okay, so as you know, transductive learning refers to the kind of supervised learning that you can carry when, at training time, you exactly know your test. You know, you already know the unlabeled data that you need to issue predictions for, and you know that you will not need the model you trained to issue other predictions. Okay, so of course, I mean, knowing your test set in advance, knowing your unlabeled data in advance is advantageous. Okay, so you don't have its labels, but you have their covariates. Okay? So because of this, in classification, transductive classification methods have been proposed, but in a sense, also in quantification, there are many tasks which have a transductive character. Say, a customer might give you a very large data set and ask you to investigate, you know, class distributions on that data set only, you know, so that's a transductive context. Very little research has been going on transductive quantification methods. We might say that the Serens-Latin-Decastecker algorithm has a sort of a transductive character because it takes an unlabeled data set and essentially iterates on that data set only. So more research on these kind of methods should be done. Okay. So another area is, of course, deep learning. Okay, so deep learning is dominant today in machine learning, but still, let's say the amount of quantification methods that are specific of deep neural networks are still a minority. And probably there is a lot of still of untapped potential in deep learning for quantification. Another area which needs investigation is explainability. So there is a lot of push for generating explainable machine learning model, explainable classification models and methods in the literature, and of course, I mean, the same goes for quantification methods. Okay, so far no paper has ever been published on explainable quantification methods, but it's quite clear, you know, that having methods, you know, that can explain why they issued that prediction, you know, that class prevalence value might be valuable. And also, you know, possibly the most burning questions of all is investigating the relationships between quantification and types of data shift other than prior probability shift. You may have realized, through these classes that prior probability shift is the dominating type of shift in quantification research, essentially because the artificial prior protocol, which is the protocol that everybody uses in order to evaluate quantification methods, is a protocol that simulates prior probability shift. It, say, generates samples characterized by different class distributions, okay? And but there are other types of data that shift, okay? So in the real world, we might train a quantifier and we might need to apply a quantifier on data which are very different from the ones that we have used for training it, and how different they are, defines the type shift, okay? So are they different just in terms of the class label? Or maybe, so that's prior probability shift, but there is also covariance shift, there is concept shift. So more research on quantification and on their robustness to these other types of shift is needed. So let me come to the conclusions of this course. Conclusions, of course, that will just only precede the hands-on session that Alejandro will start in a few minutes. So what are the conclusions? Well, let's say that we hope we have given you a sort of an overview, a reasonably interesting overview of the quantification fields nowadays. We hope we have passed the message that quantification is important because it can deliver much higher estimation accuracy than classify and count, okay? And in general, there is a growing awareness that quantification will be more and more important. And one of the reasons is that there are more and more data in digital form. And because of this, there will be more and more application contexts in which we will it will simply not be possible to analyze data at the individual level. But what we will need to is, data analysis at the aggregate level. There will keep coming up contexts in which, say, because of the millions of individuals that we classify, we will not, as users, be able to analyze the class label that has given to a given individual. So when data comes by the millions, it is in the case that the only analysis that we can afford is at the aggregate level. So in general, the takeaway message to users of supervised learning should be that, let's say, when you're using classification and your only goal is to obtain aggregate results, that means class prevalence estimates, well, in this case, your work would probably benefit from using quantification technology, say learning to quantify technology, instead of simple classification technology. Okay, so this is a good moment for questions, if there are any, before we move to the hands-on session. Are there questions, either on today's class or on the previous classes? If there are no questions, I will stop sharing and pass the mic to Alejandro, who will give you the hands-on session. Okay, I should have stopped sharing, Alejandro?
Yes, I think so. Okay, let me start sharing now. Okay, can you see my screen now?
Yes, we can.
Okay. Okay, so the goal of this tutorial is to showcase how to create a basic quantifier for sentiment polarity. And so for the sake of simplicity, we will here restrict our attention to the binary case. But you know, everything we say here applies quite straightforwardly to the single label case as well. Okay, so first of all, I will then when the course is finished, when the course is over, I will share with you all this code, so you don't have to set up your environment now. So just follow the lecture. Okay, so here there is some boilerplate code in which we give permission to Google Drive in order to have access to a local file system. And then we here simply download a data set that I have prepared. We unzip the data set and we then simply remove the zip file. This could take some minutes. Okay, so we have the data set. Okay, these are some imports of stuff we will be using. Okay, so first of all, let's take a look. Let's load the data set and take a look at its content. So, and the data set we have downloaded is a label collection, which consists of a list of documents in which we have one document per line, following a format which is very simple, in which we have a number 1 or a number 0 for indicating that the document is positive or negative. Then we have a tab character, then we have one line in which we have the text, and then we simply have an end line. So this is the code that processes this kind of inputs. So let's simply define this function in Jupyter, and let's simply load our data set. So this function returns every time we call it, it returns a list of documents and a list of labels. So we have the training documents, we have the training labels, and we also have the test documents and the test labels. Okay, so let's take a look at the data set. Here I am printing 5 documents, the 5 first documents in the data set, in the training set. So as you can see, we have, for example, the first one is the negative one, and this is the text which is included in the review. I haven't said it, but these are Amazon reviews of Kindle devices. So this is the text which is attached to this label, in this case negative, and you know, we can see other 4 documents. Okay, so we have the data set. Let's take on the first exercise, in which we are gonna implement the most basic quantification method, which is a classify and count. Okay, so the first thing is, because we have our documents in text form, we should transform them into vectors. You know, there is a pretty simple way for doing this using scikit-learn. I don't know if you are familiar with scikit-learn, but what we are going to be using here is a function that computes the bag of words model using TF IDF weights. I don't know if you are familiar with this terminology, but these are things that somehow fall outside the scope of this course. So for the moment being, let's simply assume that we have this function that transforms text into numerical vectors in a high dimensional vector space. And let's take a look at the shape of this matrix. So XTR stands for the training matrix, the covariates of the training set. So in this case, we have more than 3,800 documents, each of which has something like 4,400 dimensions. We do the same thing for the test. And we have more than 21,000 test documents, each of which has, of course, the same dimensionality. So 4,400 dimensions. Okay, so we simply convert labels into NumPy arrays. This is for convenience, because we now can leverage some functionality which is implemented in NumPy. So for example, because our labels are binary, so we have 1 for positives and 0 for negatives, computing the prevalence of the positive class actually amounts to computing the average or the mean of these vectors of labels. And this is exactly what we are doing here. So we are getting the training prevalence and the test prevalence by simply computing the average of these two NumPy arrays that contain the labels of each of the documents. This code simply prints them so that we can read them more easily. So we have a training prevalence of 91.9%, while we have a test prevalence of 93.7%. Of course, we know the test prevalence because this is a data set for experimental purposes and so on. But in real cases, at most we know the training prevalence. Of course, we do not know the test prevalence. Okay, so classify and count actually comes down to simply training a classifier on the training set. This is exactly what we are doing here. So we are importing the implementation of linear support vector machines, which is made available in scikit-learn. We simply create one support vector machine here, and we train our classifier using the training matrix and the training labels. This should be very quick. Okay, we have our classifier trained on the training set, and we can now simply use our classifier, our support vector machine, to issue predictions on the test documents, which are in XT. Okay, so that's done. We have the predictions in this NumPy array, which is called YT, standing for test, and HAT, standing for predictions. These are estimations. And again, we can compute the prevalence of the positive class by simply computing the average of this vector. This is what we are doing here. So we have the estimated prevalence in this variable. We have the true prevalence in this other variable, and let's simply print them both. Okay, so we have a true test prevalence of 93.7%, just as before. And we have an estimate of 97%. And in terms of absolute error, this means that we have an error of 3.3%. Okay, so 3.3% is actually not that bad. It's something that we shouldn't have expected, because we have been saying that classify and count is not a good quantifier, but this prediction is not that bad after all. So let's try to better understand what is happening here. Okay, so in this part we are going to be dealing with evaluation, and this function here simply plots the so-called 4-cell contingency table, which is a table summarizing the classification effectiveness in terms of true positives, false positives, the false negatives, and the true positives. Okay, so this is the 4-cell contingency table, or the confusion matrix of our classifier. So we have that our classifier predicts or is characterized by more than 20,000 true positives, 800 false positives, 158 false negatives, and 500 true negatives. Okay, here we can show the statistics. In this case, we are printing the true positive rate and the false positive rate, also the accuracy. These are the formulas that implement these quantities out of the true positive, false positives, and so on and so forth. So actually the true positive rates amounts to computing the rates of positives, of actual positives that have been correctly classified as positive by our classifier, while the false positive rate amounts to computing the fraction of true negatives that our classifier has mistakenly taken as positive. Okay, so yeah, let's simply run this cell of code, and these are the quantities that we wanted to show. So we have a true positive rate of 0.99. We have a false positive rate of 0.63. The average, the accuracy of this classifier, which is computed in terms of the fraction of correctly classified instances over the total number of instances, is quite high. Actually, is about 95% of accuracy. Okay, so so what is happening here? Let's print again these quantities, and let's take a closer look at them. So we have estimated a prevalence of 97%, but the training prevalence was 91%, while the test prevalence was 93%. So note that while the absolute error of classify and count is actually 3.33%, we would have made a smaller error. We would have achieved a much better accuracy if, instead of using the predicted prevalence value of classify and count, we had simply taken the training prevalence as an estimate of the test prevalence. So if we hadn't even take a look at the test set, we have simply relied on the training set, and we have predicted the test prevalence to be the training prevalence, we would actually had made a smaller error. This technique would it's something that in literature is called the maximum likelihood prevalence estimator. And it's actually, you know, it's a no method. It's a method that does nothing. It's a method that simply assumes or relies on the fact that prevalences may not change and simply reports the training prevalence as an estimate of whatever sample is provided. So, you know, having a method which works worse than the maximum likelihood prevalence estimator means that the method is not very good. It's not a very good one. So this 3.3% we have observed before is not actually that good. And, you know, of course, this is happening because we are testing the accuracy of our quantifier on a test sample which is, you know, which has been drawn from the same or from a very similar probability distribution with respect to the training set. So, you know, in machine learning, the training and the test samples are assumed to be IID. It's standing for independent and identically distributed. And, you know, in these cases, we are not facing prior probability shift. Of course, we would not even resort to quantification if we could assume that the training and the test data be IID, or, you know, in other words, we use quantification in cases in which we know or we assume or we believe that there is some kind of prior probability shift, some change in the distribution of priors. And, you know, this means that the kind of evaluation we have done so far is flawed. It's not a correct way of measuring the accuracy of a quantifier, because, you know, the evaluation metrics should be in agreement with the task. We should use measures that take into account the effectiveness of the quantifier against, you know, widely varying amounts of shift, of prior shift. And, you know, the most simple way of doing this is by means of the artificial prevalence protocol that we have seen during the lectures. This is a function that simply computes all the prevalence points on which we would like to test our quantifier. You can see that the output of this cell is something like is a NumPy array in which we have 1%. We have many 1% because we want some repetitions of the same number of prevalence. So actually this is a vector in which we have 0.1, 0.1, 0.1, so many times. Then we have 0.2, 0.2, 0.2, so on and so forth, until we end up having 0.99%. So these are the prevalence values we want to test. And this piece of code here is an abstraction of a data structure that, you know, for simplicity, I have simply called label collection. You know, this is a data structure that simply takes care of either the training set or the test set as a single entity. So we have the positive instances, we have the negative instances. This data structure actually also knows how to compute the size of this sample. It knows how to compute the prevalence of this sample. Again, this amounts to computing the average. But there are some functions which are convenient for performing sampling. And I'm not going into the details here, but out of a label collection, we can ask for a sample of size with a specific prevalence. This function simply checks, this is a sanity check for guaranteeing that the prevalence is in between 0 and 1. And then, this function computes how many positives should be drawn from this distribution or this sample, how many negative documents should be drawn from this sample. And, it simply performs a random choice using functions from NumPy, and it takes, the number of positive requested out of the positive documents, and so on and so forth. So this piece of code actually is computing, is generating a sample out of our labeled collection, in which we have artificially forced one specific prevalence value on one specific size. Other functions which are implemented in this class is split stratified. Okay, is split stratified. This will prove convenient when doing some experiments. So for those of you who are not familiar with split stratified stratification, this is a way for performing partition of a data set, in which we indicate the proportion of the training set and the proportion of the validation set, which is implicit because this is a partition, so all parts should sum up to the original sample. So this splitting function, which is actually doing is generating a partition so that the two parts of this partition have approximately the same prevalence. This is what stratification means, is that both parts are characterized similarly in terms of the response variable, in this case, in terms of the prevalence. And this function is simply a function that generates samples out of our label collection following the artificial prevalence protocol that we have seen that Fabrizio has explained during his part of the lecture. So this function is now very simple. It simply iterates over the prevalence values we want to test, and these are returned by this function artificial prevalence sampling that we have seen before. And then for each prevalence value, we simply generate a sample respecting or reflecting this prevalence, and we ask this sample to be of this particular sample size. Okay, let's simply define this class so that it becomes available for us. And now we can simply transform our training set into a label collection object, the test set into another label collection object, and we can now simply iterate, so generate many samples out of the test sample and confront our classify or our quantification method with these samples to see, to compute the effectiveness of the predictions. And this is exactly what this part of the code does. So in particular, we are generating 2,100 and 100 test samples with widely varying prevalence values ranging from 1% to 91%. And again, we have simply predicted the labels for each individual instance using our support vector machine and computing the average as a way for getting the prevalence values. We can now compute not the absolute error, but the mean absolute error across all these examples that we have generated, in terms of the difference between the true prevalence and the prevalence that we have estimated. We compute the absolute difference between these two quantities, and then we report the average. This is the definition of the mean absolute error that is here called MI. Okay, so now that it is defined, we can compute the mean absolute error between the true prevalence values and the estimated prevalence values. This is what we have done here. So let's take a look. Okay, so the mean absolute error of classifying count is actually, is 31%. So in other words, our classifying count method produces an average absolute error of 31% when the artificial sampling protocol is applied. And remember that our first estimate was 3.3%. So, when things are not IID, or when we are in presence of prior probability shift, or when we are in presence of high variations in the prevalence values that we could encounter in test scenarios, classifying count actually produces an error which is, very high. So let's take a closer look to what is happening here. This piece of code, I'm not gonna explain it in detail because this is only for plotting the errors using the diagonal plot that Fabrizio has explained to you. So let's simply try and plot the distribution of errors that we have computed. Okay, this is too big. I'm gonna try and, well, maybe you can say it. I don't want to spend time in trying to reduce this. Okay, anyway, so this is the diagonal plot in which we have the true prevalence in the x-axis, and then we have the estimated prevalence in the y-axis. So the plot is called diagonal because, the perfect quantifier should be something that goes into this main diagonal. And this is the performance of our classifying count. So you can see that classifying count is actually overestimating the true prevalence most of the times. So what is happening here, as you can see, there are two additional dots, which are the true prevalence, the training prevalence, and the test prevalence. So as you can see, when the test prevalence is close to the training prevalence, classifying count does not actually performs that bad. But as long as we move away from prevalences that are different from the training prevalence, the error is bigger and bigger. It's this part of the plot here. So in other words, we say that classify and count delivers bias estimators of class prevalence, because it's biased because it tends to stick to the training prevalence it has observed during training. And if the test prevalence is not close to the training prevalence, then the estimation will be not that good. Okay, so let's move to this part of the code in which I am simply trying to wrap up things to create some kind of abstractions here. So we are gonna define this base quantifier data structure, this class, in which we are gonna say that a base quantifier is something that implements the fit method that takes as input a label collection, is something that implements the predict method, which is not defined here because every method should be responsible of this definition. And because we are gonna be reviewing the aggregative quantifiers, we will assume that there is a classify step in which we train a classifier, we issue label predictions for any test sample. So once we have our base quantifier meta class, we can define our first quantifier, which is this classify and count. And this classification, this implementation is pretty straightforward. We have already done this in a non-structured way. So this is how we should actually implement a quantifier. So in this case, classify and count is something that in the constructor simply takes any learner. In this case, for example, in support vector machine, during training, it simply fits the classifier using training data, which are these data.documents, data.labels. At prediction time, again, it simply classifies all the instances in the test set, and then simply, computes this count method, which simply reports the average of the prevalence of the labels, just as before. Okay, so here for convenience we can implement this method that is is for performing experiment, for using whatever quantifier we have, using whatever text collection we have. And this is simply a very simple function that simply iterates over test samples produced out of the original test sample. And it simply stores keeps track of the true prevalence of each sample, and keeps track of the prevalences that are estimated by our method. This is more or less the same we have seen before. And then we implement this evaluation report, which is simply a way for printing the mean absolute error of whatever method we use. Okay, so let's put everything together. This is nothing new. This is only something more conveniently implemented. So here we are doing exactly the same. We are computing test samples. We are testing our classify and count method, and we will simply plot the predictions. In this case, we are also testing one possibility. So we are asking ourselves whether the results we have seen before actually depend on the hyperparameters of the classifier, in this case, the hyperparameters of support vector machines. And you know, one of the hyperparameters which is more important for support vector machines is this variable C, which you know is responsible for balancing or trading off between classification accuracy and regularization. So trying to keep margins which are as large as possible against trying to produce a few number of errors. So what we can see here in this plot is that this is not the case. So the results we have observed so far, you know, are not consequences of a bad choice of these C parameters. Because, you know, when we explore many such configurations for C, we end up getting results which are more or less the same or dramatically worse, but not better. So in any case, all these quantifiers, all these classify and count quantifiers are strongly biased quantification methods. And this is irrespective of the quality of the hyperparameter tuning. Okay, so I hope I have convinced you now that classify and count is actually not the good way to go. So let's move to other more sophisticated quantifiers. Here I'm simply regenerating the plot because we are gonna need it. And okay, so the first method that we are gonna explain here is the adjusted classify and count. So one way to improve over the results of classify and count is, you know, imagine that we know that our classifier tends to say yes more often than no. Or so the question here is it possible to apply some kind of correction or some kind of adjustment to the final prediction? So this is the main idea behind the adjusted classify and count. This is a method we have already seen during the lectures. So the idea is the following. So the idea is that, you know, the prevalence that we estimate by a classify and count is, you know, obeys this formula here. So the prevalence we obtain is the true prevalence by the true positive rate plus the negative prevalence, or the prevalence of the negative class, multiplied by the false positive rate. Does this make sense to you? So what we are observing is, you know, the true prevalence. This is weighted by the the true positive rate, and this is weighted by the true prevalence. But we are also summing the false positive rate in a fraction that depends on the negative class. So another way of saying this is that the P estimate is the true prevalence multiplied by the true positive rate plus the negative prevalence multiplied by the false positive rate. And, you know, we can simply use this formula and solve for the true prevalence instead of for the predicted prevalence. And this give us this estimate here. Okay. And of course, we don't know the false positive rate nor the true positive rate for a classifier, but this is what adjusted classify and count tries to estimate. So the idea is to estimate these two quantities and then apply this formula for getting the true, or an estimate of the true positive prevalence. Okay, so this is how we implement this method. This is the adjusted quantification, which simply, comes down to implementing this formula. There is some other sentences here that simply keep, this is a safety check, just to guarantee that we are not divided by 0. And this is a clipping function because, there is, if our estimates are not good estimates, it could well happen that our estimation falls outside the range 0, 1. So we simply implement this heuristic here in which we clip the values to 0 and 1. This is the adjustment. This is how we estimate the true positive rate using simple NumPy functions. This is how we estimate the false positive rate. And, now that we have these functions, we can simply implement our adjusted classify and count quantifier. So this comes to another base quantifier that, internally has a classify and count. When we fit the method, we first create a validation set using this split stratified function that we have seen before, so that we now have a training set and a validation set that we will use. So of course we will use our training set for training the classifier, in this case our classify and count quantifier, and we will use our validation set in order to get estimates of the true positive rates and the false positive rates using, these two functions that we have seen before. Once we have our estimates, TPR, FPR, we can simply compute the prediction of the adjusted classify and count by invoking this adjustment that we have seen before, giving us input our estimates of the true positive rate and the false positive rate. Again, the classifying function simply comes down to classifying all the instances. Okay, so now let me define this method. Okay, so now that it is defined, we can simply use our classify and count method using our, the function that simply confronts the classify and count method with all the tests. And this is what we get now. So in this diagonal plot, we have this new curve here, which is orange, in which we can see that the performance of the adjusted classify and count is much, much better than the performance of the classify and count. So the adjustment is actually working. And, the closer we get to the main diagonal, the better the method. There is quite some improvement here. Okay, so let's move to another method. This is the probabilistic classify and count. Okay, so classify and count relies on the counts or on the estimations of hard decisions, hard predictions issued by a crisp classifier. So a classifier like support vector machines, which return ones or zeros for positives and negatives. For the reasons that we have discussed in the lectures, it would be preferable to employ a probabilistic classifier. so a classifier that instead computes the posterior probabilities instead of, zeros and ones, so that we could take advantage of the belief of the classifier in that an example is positive or negative. So intuitively imagine that a classifier outputs, 0.75, for example, for all the items in a set. So, because this value is above 0.5, standard classifying count would have predicted 100% of positives, while a probabilistic quantifier would instead have predicted that 75% are actually positive, because for each of them it thinks in a way that there is a probability that a probability which is 75% of chance that the document is positive. So in average, we should prefer, to estimate that 75% of these documents were actually positives. So the problem here is that, probabilistic quantifiers need probabilistic classifiers. And in this case, support vector machines are not. So support vector machines are traditional classifiers which, work pretty well, but are not probabilistic. So we have two options here. One is to simply change the classifier and go for other classifiers like logistic regression or multinomial Bayes or random forest and other learners, other classifiers which already return posterior probabilities. Or yet another option is to calibrate our classifier. So again, calibration is an operation that we apply to a classifier in order to tune the decision function of the classifier, in order to map the decision function of the classifier into the 0-1 interval, so that this can be interpreted in terms of probability. And in particular, we say that the classifier is well calibrated when, for all the instances for which the classifier says, alpha percent, then alpha percent of them were actually positives. This is, this is the formula. This is the definition of calibration. And, we simply here use this calibrated classifier CVU, which is a function provided by scikit-learn in order to calibrate our classifier in case it is not a probabilistic one. So in scikit-learn, you typically check for this property by asking the method whether or not it implements this function, this predict proba. This predict proba is a function that returns posterior probabilities. So in case the learner, in case the classifier does not implement this predict proba, then only in this case we apply a calibration method. This calibration method is provided by scikit-learn and is based on Platt scaling, which is this method, this sigmoidal transformation that we have seen during the lectures. Okay, so this is the implementation of probabilistic classifying count. We simply calibrate the method, the classifier, in case it is not probabilistic. We then simply fit our method. So we train our classifier, and then we compute the class prevalence by, by calling this soft classify method, which is defined here, in which we instead of using the predict function of the classifier, we use the predict proba function of the classifier, so that we have posterior probabilities. Because our problem is binary, we can only attend to the positive posterior probability. So the posterior probability that the document is positive because the negative one is constrained and is the complement of this one. So for simplicity reasons, we simply take into account the positive posterior probability, and then again we compute the estimation of the class prevalence by performing the average of these soft predictions, and then again we have to clip our values into 0, 1. Well, actually, in this case, I don't think it is really necessary, but it's something that we can do without any risk. Okay, so let's try and evaluate our probabilistic classifying count, again generating many samples using this artificial prevalence protocol, and then plotting again our new method, which is in this case is in green. As you can see, the predictions that probabilistic classifying count generates are much better than the predictions of classifying count, but are much worse than the predictions of adjusted classifying count. Okay, so what we have seen so far is that moving from a hard classifier to a soft classifier seems to be beneficial, and that implementing some adjustment seems to be beneficial. So, the obvious step is to combine these two observations and implement our probabilistic adjusted classifying count. This method is very simple because it's simply, again, a combination of these two observations. So we here take as our base quantifier, we use probabilistic classifying count instead of classifying count. We again generate, by means of this split stratified function, we generate two data sets, one for training, one for evaluation that we call validation. We train our probabilistic classifying count using this training set. We estimate the true positive rate and false positive rate using soft values instead of crisp values on the validation set. And and everything that remains is to apply this adjustment using, in this case, PCC as an initial estimate of the prevalence values, and using these estimations of the true positive rate and false positive rate. So this is quite straightforward once we have implemented the other methods. And again, let's simply compare the performance of probabilistic adjusted classifying count. Okay, so this is what we get now. So we have this new red line, which represents the performance of probabilistic adjusted classifying count. As you can see, the both advantage, both benefits, both improvements are somehow accumulated in this new method, which performs much better than any other classifying count variant. Okay, so we have also some numerical values here. So as you can see, the mean absolute error of our classifying count was something around 21%. Then we have the mean absolute error of adjusted classifying count, which is reduced to something around 11%. Probabilistic classifying count, and that's an error of around 26%, while our probabilistic adjusted classifying count only scores an error of something like 4.2%. So it's much, much better. Okay, so the last part of this lecture concerns the implementation of expectation maximization for quantification. This is the method that is sometimes called Latin sirens, Decker algorithm, which are, or LSD for the initials of the inventors. And this is this method we have seen during the lectures, in which we apply an expectation and maximization algorithm, which is an iterative and mutually recursive method for estimating the priors using the posteriors, and then updating the posteriors using the last prior, and so on and so forth, until the method reaches convergence. Okay, so this is simply the implementation of this method. It's not worth going into the details. I will share with you this code so you can take a closer look at this implementation. But it's simply computing this while loop, in which we have this A step standing for expectation step, in which we simply update the prior, which is the prevalence. Then we have this M step, which stands for maximization step, in which we update the priors. Sorry, I have you got it. So during the M step we update the priors. During the E step we update the posteriors, not the priors. Okay, so let's simply define the method, and let's simply compare the performance of this method against all other methods. Okay, so this is what we got here. So as you can see, the EMQ method in this case is this purple line, is much, much better than any other method in this comparison. So you can tell because the EMQ is fairly close to the optimal or the ideal quantifier here. So it's almost always on top of this main diagonal. Numerically, the EMQ or the LSD method makes an error which is 1.8% using this aggressive, artificial prevalence protocol. So this is an indication that our method works very well. That's all for this part of the lecture. Again, I will share with you the code, maybe with some additional explanations in order to facilitate the comprehension of this example. And that's all for today, I think. Okay, so maybe this is a good time for taking questions, if there is any. If otherwise, just simply we will go on the next Thursday. There is another hands-on part, but I think it's not gonna take much of your time. It's something that I think we can cover in less than 1 hour or so. That's all. If there is no any question, no further comment, I will tell you. That's all. Fabrizio, you want to say something?
No, everything okay. So see you next Thursday at 10 a.m. Okay. Bye all.
Bye-bye.
Bye.
Thank you. Bye.